One of the key ideas in linear algebra, especially at the beginning, is the ability to differentiate between linear independence and linear dependence of vector sets. So let's start by talking about the definition of linear independence. An indexed set of vectors v1 to vp in Rn is linearly independent if and only if the vector equation x1 v1 plus x2 v2 plus xp vp equals the zero vector has only the trivial solution, meaning that all x's, or all weights in this equation, are equal to 0. In other words, if we were to take this vector equation and condense it into the matrix equation ax equals the 0 vector, then we would see that we only have the trivial solution. So let's compare that to linear dependence now. An indexed set of vectors v1 to vp in Rn is linearly dependent if and only if there exists weights c1 to cp, which are real numbers by the way, not all equal to 0, such that c1 v1 plus c2 v2 plus cp vp equals the 0 vector. In other words, if we were to take this vector equation and write it as a matrix equation, ax equals the 0 vector, we would see that ax equals 0 always has a non-trivial solution. And this is only possible if one of these weights, c1, c2, c whatever, if one of these weights is a non-zero number. Definitions can really sound like gobbledygook sometimes, so let's talk about the geometric side of this for a second. So we're going back to the linearly independent side, and this is our visualization of the definition just in R2. So whenever we're in R2, we have two vectors involved. And if we're talking about linearly independent vectors, we're talking about vectors that are not multiples of each other. They do not fall on the same line. And this is easy to remember because when we think of independence, even just our English definition, we're thinking of something that wants to go its own way. So linear independent vectors want to go their own way in R2. They are not multiples of each other. On the other hand, in R2 for linearly dependent vectors, again, still looking at two vectors, linearly dependent vectors are multiples of each other. They actually fall on the same line if we think about this in an Algebra 1, y equals mx plus b perspective. They're just an extension of the same line. Again, this kind of makes sense when we think about the definition of dependence, even in English, things that need each other, rely on each other. These two vectors rely on each other to form the same line. Now things get a little bit more interesting when we move into the third dimension. So here's R3. We're going back to linear independent vectors now. And we have vector u, 3, 1, 0, vector v, 1, 3, 0, and vector w, 0, 2, 3. Notice that w is not in the span of vector u and v. If you go back in your mind and remember your definition of span, you'll remember that span means algebraically, I should be able to add some multiple of u and some multiple of v together to get vector w. We can see, however, that's clearly the case. Disregarding the trivial solution, there's no number that we can pick to scalar multiply vector u or scalar multiply vector v to create vector w. Geometrically, of course, we can see that vector w is not the result of adding u and v in their multiples. It's actually going completely its own way, which again falls into the idea of linear independence. We're kind of picking on vector w here being not in the span of u and v, but we could say the exact same thing about vector u. Vector u is not in the span of w and v, and vector v is not in the span of w and u. So regardless of which vector that we're looking at, we notice that none of them are in the span of the other one. So all three of these are linearly independent. Back to linearly dependent vectors now. So we're in R3 still, we're looking at three vectors. Vector u is 3, 1, 0, vector v is 1, 3, 0, and now vector w is 4, 4, 0. So we can see just by the dimensions of these vectors that adding u plus v would give us w. 3 plus 1 is 4, 1 plus 3 is 4, 0 plus 0 is 0. We could also see that using tip-to-tail addition method, we could generate vector w from u and v. This means that w is in the span of u and v. So these are linearly dependent vectors. Now, all that's required of a vector set to be linearly dependent is that one of the vectors resides in the span of the others. So of course we can tell by looking at this that vector v is not in the span of u and w. However, that doesn't really matter because w is still in the span of u and v, and as long as one of those vectors is in the span of the other two, we're okay, and these are linearly dependent. Alrighty, so quickly to summarize what linear independence is, whenever we're looking at an index set of vectors in a vector equation, if we rewrite that as a matrix equation, ax equals 0, we're looking at only the trivial solution. In R2, we see that the vectors are not multiples of each other and don't form the same line. In R3, we see that the vectors are not in the span of one another. W is not in the span of uv, but also u is not in the span of vw, and v is not in the span of uw. A couple quick notes at the end. Vectors are not multiples of each other. The 0 vector is never included in the index set for linearly independent vectors. And finally, there are never more vectors than entries in each vector. So I've abbreviated the vectors p and the entries n, and just kind of given a little diagram of what that looks like. Could be a 3x3 matrix, might be linearly independent. We just know that p is always going to be less than or equal to n for linearly independent vector equations. Now, just because p is less than n, just because there are not more vectors than entries in each vector, does not necessarily imply it's linearly independent, but that is just a characteristic that we want to kind of keep in mind. It's still important to check the other characteristics. And finally, summary of linearly dependent vectors. So for linearly dependent vectors, whenever we have that vector equation, we can rewrite it as in matrix equation, ax equals a 0 vector, and we'll always find that we have a non-trivial solution. Non-trivial solution requires that at least one of those weights, at least one of those scalar multiples in front of the vectors v, is going to be a non-zero number. From a geometric perspective, in R2, we're going to have two vectors. They're going to fall onto the same line, which means that they're multiples of each other. And in R3, we're going to have three vectors. And that means that at least one of the vectors is in the span of the other two. So in our visual here, we see that w is in the span of u and v because we can add u and v to get w. It would also be possible geometrically to say that there are a vector pair in a linear dependent set that are actually multiples of each other. Linearly dependent vector sets can also contain the 0 vector, which linearly independent sets can never have the 0 vector. So that's an interesting distinction. And finally, linearly dependent sets may contain more vectors than there are entries in each vector, but they don't necessarily have to. So we can have linearly dependent sets that are 3x3 matrices, and that's totally fine. We can also have linearly dependent sets that are 3x4 matrices where p is greater than n. The number of vectors is greater than the number of entries in each vector. Not a requirement, but that is the place where it could show up. So that's a summary of linear independence versus linearly dependent. Let me know your thoughts if you have any. Thanks for watching.